Now, what are the basis and dimension? Actually, first of all, basis is the basis is the vector space B, and S is the any set B1, B2 dot dot up to Bn. So, if two conditions are satisfied with the subset S of vector space B is called basis. That means S span B, that means span B, that means B can be written as a linear combination of U, where U is the element of B and has a solution after echelon form and whose determinant of matrix A will not equal to 0. And S can be written as S is linear and independent. So for linear combination summation Ci Bi is to x equals to 0, there is only a trivial solution where determinant of A is not equal to 0. In that case, S is called basis. So basis will be a spanning of sets and linearly independent of sets. A basis S must have enough vectors to span B, but not so many vectors that one of them could be written as a linear combination of the other vectors. So the standard basis for R3 IJK can be written 1 0 0 0 1 0 and this, and the standard basis of Rn E1 E2 E dot En E1 equals to 1 0 0 1, E2 equals to 0 1 0 0 in this case. So for example R4 this one. Now the standard basis for matrix will be 2 cross 2 matrix 1 0 0 1 0. This is the 4 types of 2 cross 2 matrix. A standard basis for polynomial and degree polynomial 1 x squared dot dot up to x to the power n. And for the polynomial of 3 third degree polynomial, the standard basis will be 1x squared and x cubed. Now the non-standard basis for R3 show that S equals to B1, B2, that means 1, 1 and 1 minus 1 is the basis for R2. How we can show? First of all, taking U equals to U1, U2 belongs to R2 space, then the linear combination U can be written as this. Okay, U is the sub equals to U1, U2. This is why C1 plus C2 equals to U1 and C1 minus U. Just because the coefficient matrix of the system has a non-zero determinant, the system has a unique solution for each U. Thus, you can conclude that S spans R2. Again, linear combination equals to 0. Then we get C1 plus C2 equals to 0 and C1 minus C2 equals to 0. Now solving, we get the non-zero determinants. So you know that the system has only a trivial solution. Thus, we can conclude that S is linearly independent. So according to the above two arguments, we can conclude that S is basis of R2. And it is non-standard, of course. Now, uniqueness of basis representation for any two vectors. If S is the S equals to B1, B2 dot dot Bn is a basis for vector space B, then every vector in B can be written in only one way as a linear combination vectors in S. Since S is a basis, so we get two conditions. One, span S equals to B, and second condition, S is linearly independent. So span S equals to B. Let B can be written as a linear combination with the scalars C1, C2 dot dot Cn, and B another vectors with the linear combination of scalars B1, B2 dot dot up to Bn. So B plus minus 1 into B equals to 0. So we can write B minus B can be written as like this. S is linearly independent with only a trivial solution. Coefficient of Bi all are 0. Okay. So from this statement, we can show that C1 minus C1 minus B1 equals to 0, C2 minus B2 equals to 0, and Cn minus Cn. So all are equal. That means unique basis representation. Theorem basis and linearly dependence. If S is the basis for a vector B, then every set containing more than n vectors in B is linearly dependent. In other words, every linearly independent set contains at most n vectors. Let S1, U1, U2 dot dot up to Um, where M is greater than n. So span S equals to B. U1 equals to linear combination of the first row, and U2 equals to linear combination of the with the scalars of second row's elements. And in this way, we get UM with the last row of the linear combination of C1M, B1, C2M, B2 plus dot dot CNM, BN. So all UI can be written as the linear combinations. Okay. So consider the linear combination k1 u1 k2 u2 equals to 0, or if all ki's are not all 0, so s1 is linearly dependent. Suppose d1 b1 d2 b2 equals to 0, where di can be written as the linear combination. So since s is linearly independent, so all constant will be 0, that means all di will be 0. In that case we can write the system of equation equal to. So if the homogeneous system has fewer equations than variables, then it must have infinitely many solutions. So in that case, m greater than 0. So this linear combination equals to 0 has, the system has non-trivial solution. So S1 is linearly dependent. Now number of vectors. If the vector space B has one basis with n vectors, then every basis B has n vectors. So S is equal to this and S dash equals to UM. So are two bases with different sizes for B. S is a spanning vector B, and S dash will be linearly independent vectors. So M is equal to 1. And S dash is the basis spanning B. S is set of linearly independent vectors. In that case, N is equal to. So from these two inequality, we can conclude that N equals to M. So what is the dimension? Actually, the dimension of a vector B is defined to be the number of vectors in a basis B, and where B is the vector space and S is the basis for B. So dimension B equals to number of vectors in basis vectors. Now there are two dimensional. One is finite dimensional, another infinite dimensional. A vector space B is finite dimensional if it has a basis consisting of a finite number of elements, and infinite dimensional if a vector space B is not finite dimensional, then it is called infinite dimensional. Now the example, finding the dimension of a subspace of R3 space. Suppose a W equals to D C minus DC, where CD are the real numbers, and number B, W equals to twice B 0, where B is the real number. Now for the first one, D minus C minus DC can be written as the linear combination of these two vectors 0 1 1 and 1 minus 1 0. So S equals to these two. S is the linearly independent and S spans W. So S is the basis of W, and dimension what? Number of basis vectors 2. Similarly for the second one, B can be written as a multiplicative property, that means scalar multiplication. So with the basis vector T10 spans W, and S is the linearly independent. So S is basis for W, and dimension what will be? Number of basis vectors. Now finding the dimension of subspace for M2 cross 2 matrix. Suppose A, B, C, AB and BC are the 2 cross 2 matrix, where ABC belongs to real number. So ABC can be written as the with the linear combination of unit matrix. So S equals to this 3 spans W, and S is the linearly independent. So S is the basis for W, and dimension W what? Number of basis vectors 3. So for the standard basis, show that the following sets are basis of R3 space. So S equals to 1 0 0 0 1 0 0 1 1 0. In that case, with the figure, we observe that these sets of vectors can be written as a linear combination. So has a trivial solution with all scalars equals to 0. That means S is a basis for R3. So the definition of basis for a vector space will be this: S is if a subset S is a vector space B, said to be basis B if S is consists of linearly independent vectors, and S generates B, that means B can be written as linear combination. So this is the actual definition of basis of a vector space, and this is a system of consisting of n vectors as a basis. So we can prove this one result. First, we should show that S is a linearly independent set of vectors. We have proved it in one of the previous example. So now we should prove this number of linear combination equals to Bn. We have always basis vectors is a subset of Bn. So we should prove that B is the subset of Ls. Each vectors Bn is a linear combination of elements. That alpha equals to a1 a2 dot many scalars of vectors Bn, then we can write this vector equals to linear combination of the basis vectors. So in this case, S is the basis of Bn. We shall show that we call that a standard basis for this. Similarly, we can show the infinite sets as a basis vector of polynomial integer functions. And this is the finite dimensional vector space. The vector space B is said to be finite dimensional or finitely generated if there exists a finite subset of S B such that B is the LS. Now we will try to understand what is the now we'll try to understand what is the spanning of sets, a span of sets. Let B and W be two non-zero, non-parallel vectors in R3 with their tails in the origin. This is the actual diagram. The plane M through the origin containing these vectors is described in this figure. So n equals to normal for M. And M consists of all vectors P such that the dot product will be 0. Now, while this is very useful to look the plane, now the idea follows that observe that if by the diagram the vector P is in M, P lies in M, if and only if it has the form P equals to AB plus BW. That means P can be written as the linear combination of BW vectors, okay, which passes through the origin. For certain real numbers, AB, which is belongs to real R, that means P is a linear combination of BW. Hence, we can write and describe the M vector space like M vectors where X plus BW such that AB belongs to real number. Okay. So, and we say that BW is a spanning set of for M because the BW a linear combination of BW lies completely on M. It is this notation of a spanning set provides a way to describe all subspaces of Rn. Okay. Similarly, for the given vectors x1, x2 dot xk belongs to Rn vectors of the form the linear combination where all Ti's are scalars is called linear combination of Si and the coefficient of Xi in the linear combination. So this is the definition of linear combination vectors and a span R. The set of all such linear combination is called span of the Xi is denoted by span this, which is the linear combination such that all scalar Ti belongs to real number. If B equals to a span this, then we say that B is spanned by the vectors this and that vectors x1, x2, xk span the space B. Here two examples, span of x equals to tx where t belongs to real number and the span this rx where simplify this there are x plus sy. That means xy can be written as a linear combination. Now an example, let x equals to and y equals to this 2 in R4 space. Determine P and other vectors or Q are in U span xy. The vectors P is in U if and only if P can be written as the linear combination of Sx and Ty. Where S and T are the scalars. Equating the components, we get the Fourier equations. Okay, this linear systems has the solution. You can solve this by Chillen form and P is in U. On the other hand, Q can be written as the linear combination of Sx y. This the system has no solution. So Q does not lie in U. So that means this force equation can be solvable and we get S equals to 3 and T equals to -2. But this equation cannot be solvable. This is why it has no solution. And Q, this means Q cannot be represented as a linear combination of ST. So this is not lie in wholly in U. Now, span theorem, let U equals to span x1, x2, xk in Rn, then U is a subspace of Rn containing each xy, and if W is a subspace of Rn, each xi, and then ui. So this is the proof. The zero vectors can be represented as 0, x1, and linear combination of xi. If x equals to linear combination of t1, x1, t2, x2, xk, and y also in U, then x plus y and x scalar multiplication with the vector x are in U. So closure law and scalar multiplicative law are satisfied. Finally, xi is in U. Then means, for example, x2 can be written as like this. So s1, s2, s3 is satisfied for U. That means the properties of linear satisfied. Another one, two x equals can be written as a linear combination. All ti's are scalars. Each xi belongs to w, and then tixi also belongs to w because w satisfies S3. So the x belongs to y. That means proved. So this is the span theorem. Another example. Let u, v, w are the three vectors, non-zero vectors in R3, where v, w independent, and show that u, v, w is independent if and only if u is not in the plane M. Okay, this is the whole plane M, and plane M equals to span of BW. This illustrated in the diagram. Now solution, if u, BW is independent, suppose u is in the plane. Okay, u is in the plane M and span BW. Then we can say that u can be written as the linear combination of BW, where AB belongs to real number. Then in that case, we can write this whole equation 1 into u minus AB minus BW, which contradicts the independency of the UVW. On the other hand, suppose that U is not in M, we must show that UVW is independent. If RU as B and TW equal to 0, where RST are in R3 space, then R equals to 0, since otherwise U equals to this, and U can be written as linear combination of this, where R is not equal, R can never be 0. But as B TW equals to 0 and S equals to T equals to 0, by our assumption, this shows that UVW is independent as required. So from the figure, we observe that UVW independent, okay, not dependent on other vectors, but UVW here not independent, lies wholly in the plane. But U here, U cannot be represented, can be represented as the linear combination of BW. This is why independent. And here U cannot be represented with the linear combination of BW. This is why not independent. Now an important theorem we will try to prove that there exists a basis for each finite dimensional vector space. Let B be a finitely generated vector space where let S is the alpha 1, alpha 2, dot, dot, alpha m be finite subset of B such that B can be represented as the linear combination of S vectors. So we may suppose that no member of S, if S is linearly independent, then S itself a basis of B. If S is linearly dependent, then there exists a vector alpha I which cannot be expressed as a linear combination of the preceding vectors. That means alpha 1, alpha 2, dot, dot, alpha I minus 1. If we omit these vectors alpha I from S, then the remaining set S dash contained with M minus 1 vectors. So in that case, alpha 1, alpha 2, dot, dot, alpha I minus 1, alpha I plus 1, dot, dot, alpha M. Okay, also generates B. Then B can be represented as the linear combination of S dash. For if alpha is any element of B, then B can be B equals to LS implies that alpha can be written as a linear combination of alpha 1, alpha 2, dot, dot, up to alpha m. Let alpha can be represented as alpha 1, A1, alpha 1, A2, alpha 2, dot, dot, AI minus 1, alpha I minus 1, and AI alpha, AI plus 1, up to AM alpha. But alpha I can be expressed as a linear combination of alpha 1 to alpha I minus 1. In that case, alpha I equals to this. Putting these values of alpha I in the expression for alpha, we get this putting here. AI, and alpha I putting here. These values alpha I putting here. We get this one. So thus alpha has been expressed as a linear combination of the vectors alpha to alpha I. In this case, alpha belongs to B implies that alpha can be expressed as a linear combination of the vectors belongs to the set S dash. Thus, S dash generates B and S dash equals to B. If S dash is linearly independent, then S dash will be the basis of B. And if S dash is linearly dependent, then preceding as above, we shall go get a new set of n minus 2 vectors which generates B. Continuing this process, we shall, after finite number of steps, obtain a linearly independent set of S which generates B and which is therefore the basis B. So at the most, it may happen that we shall be left with the subset S which contains only one non-zero vectors and which spans B. So we know that the set containing a single non-zero vectors is definitely linearly independent, and so it will form a basis of B. So this is the proof 1 of the theorem, existence of basis finite dimensional vector space. Now another one, dimension theorem for a vector space. If B is a finite dimensional vector space, then any two bases of B have the same number of elements. Suppose the vector space have finite dimensional vector space and B definitely possesses a basis. Let S1 equals to alpha 1 alpha 2 dot alpha m, and S2 will be beta 1 beta 2 dot beta m. So if the two bases B, we shall prove that m equals to n. That means number of dimension of S1 m and number of dimension S2 will be n. So since these can be written as the linear combination of S1 and beta 1 belongs to B, therefore beta 1 can be expressed as a linear combination of this. Consequently, let S3 another basis beta 1 alpha 1 alpha 2 alpha m also obviously generates vector space B is linearly dependent. Therefore, there exists a number alpha which doesn't belongs to beta 1 of the set S3 such that alpha is a linear combination of the preceding vectors. So this beta 1 alpha dot alpha I minus 1, if we omit the vectors alpha I from S3, then B also generates the remaining set of vectors S4. In this way, we can say that since B is the linear combination of S4 and beta 2 belongs to B, therefore beta 2 can be expressed as the linear combination of the vectors belonging to the S4. Consequently, the set S5 beta 2 beta 1 alpha 2 alpha m is linearly dependent. Therefore, there exists a number alpha j of the set S5 such that alpha j is a linear combination of the preceding vectors. Obviously, alpha j will be different from beta 1 beta 2 since beta 1 beta 2 set is a linearly independent set. If we exclude the vector alpha j from S5, then the remaining set will generate the vector space. So we can continue to proceed in this manner. Here, each step consists in the exclusion of an alpha and the inclusion of beta in the set S1. So obviously, the set S1 of alphas cannot be exhausted before the set S2 and betas. Otherwise, vector space B will be a linear span of the proper subset of S2, and thus S2 will become the linearly dependent. Therefore, we must have M cannot less than N. Interchanging the rules of S1 and S2, we shall get that N cannot be less than M. So in this way, we can show that N equals to M. For example, for the vectors B3, the sets S1, S2 are the bases can be easily be seen. Both these contains the same number of elements. Okay, this is the unit basis vectors. Now another theorem with the linear combinations. Let S equals to B1, B2 up to Bn be a subset of a vector space B, and Ls is the set of all linear combination of the vector in S, is a subspace containing S, and if W be any other subspace containing S, then the linear combination of set S will be the subset of W. That means Ls is the smallest subspace of B. So proof, we can write every elements B1 belongs to S as Bi equals to 1 into Bi. That means B1 can be written as 1 into B1 plus 0 into B2 plus 0 into B3 plus dot plus 0 into Bn, which belongs to Ls, linear combination sets. Similarly, we can show that Bi belongs to Ls. In that case, S is the subset of Ls. Secondly, let B can be written as the linear combination A1 B1 A2 B2 plus and Bn. So W can small w B1 B1 U1 B1 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 B2 B2 and Bn will be the belongs to Ls. Since B belongs to Ls and W belongs to also Ls, so the closer law, that means U plus W can be written as A1 B1 plus and Bn and B1 B1 up to Bn. That means after adding A1 plus B1 B1, so A1 plus B1 A1 dash and A2 plus B2 A2 dash in this way, and plus BM A1 and dash Bn. So which is also linear combination with the vectors B1 B2 Bn. So that is linear LS is closed under addition. Okay, for any any vector B belongs to LS and any scalar alpha belongs to K. So scalar multiplication can be written as like this. Alpha A1 can be written as A1 dash, alpha A2 dash. In this way, alpha AN dash. So we observe that the linear combination of sets S is closed under scalar multiplication. Again, since LS is non-empty, so LS is closed under addition, LS is closed under scalar multiplication, so LS is a subspace. Furthermore, suppose W is any other subspace of B containing S. That means S is the subset of W. So B1, B2, Bn belongs to W. Now W is closed under scalar multiplication as W is a subspace. So A1, A2, N for any scalars belongs to K. We can write scalar multiplication of each vectors A1, B1, A2, B2, and Bn belongs to W. Again, W is closed under addition. So A1, B1, A2, B2, or every vectors with scalar multiple will also belongs to W. Since the linear combination of this belongs to LS, so LS is the smallest subspace of B. Now another definition, sums and direct sums. Let U and W be the subsets of vector space B. The sum of U and W, written as UW, consists of all sums small u plus small w, where small u belongs to capital U and small w belongs to capital W. That is, U plus W can be written as B such that B equals to U plus W, where U belongs to U and W belongs to W. Remember that U and W are the subsets of vector space. Now suppose that U and W are the subspace of B, then one can easily show that this is U sum U plus W is a subspace of B. So now what will be the direct sum? The vector space B is said to be the direct sum of the subspace U and W, denoted by B equals to U direct sum W. If every small b belongs to capital B can be written in one and only one way, B equals to U plus W, where U belongs to U and W belongs to W. So in that case, we can give some example. Suppose consider the vector space B equals to R3 space. Let U be the XY plane and let W be the YZ plane. That is, U equals to XY plane, where AB belongs to real number, and W equals to YZ plane, where BC belongs to real number. In R3, we can write U plus W because every vector in R3 is the sum of vectors in U and vector in W. So in that case, R3 is not a direct sum of U and W because such sum are not unique. For example, 357 can be written as 310047. And also 357 can be written as 3 minus 40097. So we get two identical sum. This is why not unique. This is why it is not direct sum. Let U be any XY plane like this and W is the Z plane, where C belongs to real number. Now, any vectors A, B, C in R3 space written as the sum of the vectors U and vector in B in one and only one way. ABC equals to AB0 and this. Actually, this is unique. Accordingly, R3 is the direct sum of UW. So R3 equals to U plus W. Now, what will be the general direct sum? The notation of direct sum is extended to more than one factor, obviously, and B is the direct sum of the subspace W1, W2, WR, written as B equals to W1 direct sum, W2 direct sum up to WR. If every vector B, small b belongs to capital B, can be written in one and only one way, B equals to W1, W2 plus W WR. So in this case, we can write the general direct sum. Now another important theorem, a vector space B is the direct sum of its two subspaces U and W if and only if B can be written as U plus W and U intersection W equals to 0 set. Suppose B is the direct sum of the two subspaces U and W, that is B can be written as U direct sum W. Then every vectors B, small b belongs to capital B can be written as the sum of the elements of U and W. So B equals to U plus W, where U belongs to capital U and small w belongs to capital U. That means W, equation 1. B can be written as the sum of elements of U and W, and that means imply B equals to U plus W for n elements B, U, and W, which satisfy equation 1. That means we can also write B equals to 0 plus B. That means 0 belongs to U and small b belongs to capital W. Also, B can be written as B plus 0, where B is the element of U and 0 belongs to W. So this is also true. Since the elements of U and W are the elements of B, as the same sum is unique, where B equals to 0, thus U intersection W is the 0 set. Suppose U belongs to capital U intersection W implies U belongs to U, also U belongs to W. We can also write that B equals to 0 plus B, where 0 belongs to U and B belongs to W, and B equals to 0, B plus 0, where B belongs to U and 0 belongs to, this is also true. Since the elements of U and W are the elements of B. Conversely, let B equals to U plus W and U intersection W is the set 0. So we'll show that the sum is unique. First of all, write any vectors B belongs to B and B can be written as U plus W, where U belongs to capital U and W belongs to capital W. Okay. But remember that this is the small b and a small u, a small w. Okay. We'll show that such sum is unique. Now, let B equals to U dash plus W dash, where U dash belongs to capital U and W dash also capital W. So we can write B equals to U plus W and U dash B W dash. So U minus U dash equals to W dash minus W, which implies that this U minus U dash also belongs to U and W dash minus W belongs to W. So in this case, these two belongs to U intersection W, but by condition 2, we can write that this intersection equals to 0. Okay, by condition 2, U intersection W equals to what? 0. So we can write U minus U dash equals to 0 and W minus W dash equals to 0. In that case, U equal to U dash and W equal to W dash. Hence, the sum is unique for the and B equals to U direct sum W satisfied. Now, an example, U and W with the following subspace ABC, A equals to B equals to C, where 0 BC such that BC belongs to real number, show that B equals to U direct sum W. Let ABC belongs equals to B, ABC equals to can be written as linear combination of this. Thus, A belongs to U and 0, this belongs to W. So B can be written as U plus W, which satisfy B, the linear sum. Okay. Secondly, let ABC belongs to U intersection W. So thus this ABC belongs to U, also ABC belongs to W. So A equals to B equals to C, because intersection equals to 0. Hence A equals to 0 and B equals to C. So if A equals to 0, then B equals to 0 and C equals to 0. That means B can be written as the 0 vectors. So these 0 vectors belongs to U intersection W, which conditions satisfy this condition. So hence we can say that R3 is the vector are the direct sum B U direct sum W. Now what is the row space? Let A be any m cross n matrix in the row of A in R1 first row, R2 second row up to mth row may be viewed as in field can. This A, the row space of A can be written as the linear combination of R1, row 1, row 2, row 2, row 1. That is, A is the subset of can. Similarly, column space of A can be written as this. Okay. Now another important theorem of linear combinations. The set of vectors b1, b2, bn are linearly dependent if and only one of them, bk, is linear combination of the preceding vectors. Suppose bi can be written as the linear combination a1, b1, a2, b2 plus ai minus 1, bi minus 1. So this can be written as this whole minus bi equals to 0. Okay, plus 0 into bi plus 1 plus up to bi, 0 into bn. Since the coefficient of bi is equals to -1, coefficient of bi what? -1, which is not equal to 0. That means the given vectors are linearly dependent by the definition of linearly dependent vectors of vector space. Now conversely, let the vectors are linearly dependent. So scalars, the field not all 0, such that a1 b1 a2 b2 dot ak bk ak -1 bk -1 0 into bk plus 1 dot dot up to this. Suppose k be the largest vector such that ak doesn't equals to 0. In that case, we can write all elements equals to 0. In that case, the linear combination can be written as a1 b1 a2 b2 dot dot ak bk 0 bk plus 1 0. So this can be dividing by ak on both sides. We get bk equals to this one. So, but minus a1 by ak can be written as a1 dash, minus a2 by ak can be written as a2 dash. In this way, minus ak minus 1 divided by ak can be written as ak minus 1 dash. So bk minus 1. And this bk is a linear combination of the preceding vectors. Okay, this is the preceding vector because the number of elements will be bk minus 1 and ak minus 1. This is why preceding vectors. Now another important theorem: every basis set of vector space contains the same number of elements. Let B be the vector space of dimension n, and e1 e2 dot dot en be the basis of B. Suppose f1 f2 dot dot fn and the basis of B. So now we will show that f1 f2 dot dot fn contains exactly n elements. If f1 f2 dot dot fn contains more than n elements, then f1 f2 dot dot can not be basis, as B is a f n dimensional for which n plus 1 or more vectors are linearly dependent, which contradicts the fact that f1 f2 dot dot fn is a basis. Okay, again, if f1 f2 dot dot contains less than n elements and a basis, then e1 e2 dot dot cannot be basis of B, which contradicts the fact that B of the dimension n. So f1 f2 dot dot contains exactly n elements. So this is the proof. Let B be a vector space, a finite dimensional vector space of dimension n, then any set of n plus 1 or more vectors is linearly dependent. Now we have dimension of B equals to n. Suppose s equals to e1 e2 dot dot en and dimensional basis vector of B. The set of s generates or span the vector space B. That means linear combination equals to B. Now let another vector t b1 b2 dot dot br be a subset of the vector space. So where r greater than n, equation 1. If t be the linearly independent, then by the replacement lemma we also have that n greater or equal to r, since linear combination ls is bigger than the vector space. But this is impossible, since by equation 1 we get r greater than 1. Therefore t must be linearly dependent. Thus the set T containing n plus 1 or more vectors is linearly dependent. Now another important theorem: if B be a finite dimensional vector space which is direct sum of its two subspace U and W, then prove that dimension of B equals to dimension of U and dimension of W. Suppose dimension of B equals to n. Since it is the dimensional, then finite dimensional, and the dimension of U and W are also finite. That dimension of U equals to m, which is less equals to n, where n is the dimension of what? B. And another subspace of B, W, dimension W will be L, which is less than or equal to n. Suppose U1 U2 dot dot Um will be the basis of U, and W1 W2 WL will be the basis of W. Let capital B be the set combining U1 and W. Okay, will be the show that B is the basis of B. Since B contains exactly m plus L number of elements, and if B is the basis of B, then dimension of B obviously what? M plus L. As since B is the direct sum of U and W, then for any B belongs to B can be written as capital B equals to U plus W, where U belongs to capital U and W belongs to capital W. And second condition, U intersection W equals to what? 0 set. That means by using the definition of direct sum. Since U belongs to U and U1 U2 dot dot Um is a basis of U, then U can be written as the linear combination of this. Also, W belongs to W, and W1, W2, WL. By condition 1, we observe that B equals to U plus W. So B can be written as the linear combination of the whole set of U1 and W1. Now, as B belongs to, small b belongs to capital B, so B can be written as the linear combination of U1, U2, UM, W1, W2, WL. That is, B is a linear combination of the elements of B. That means B generates B set. Next, we show that B is a linearly independent set. So the linear combination will be 0. Okay, set of linear combination. Now this linear combination equals to minus B1 W1 minus B2 W2 and BL minus W. So this can be written as a summation I equals to 1 to M and Z equals to 1 to L. So this belongs to U and this belongs to W. So summation AI UI, just multiplying this same summation with U and W, we get this whole belongs to U intersection W. But by condition 2, by the definition of direct sum, U intersection W equal to what? 0 set. So which shows that this equals to 0 and this equals to also 0. That means linear combination equals to 0 and this linear combination 0. So this system of equation will has obviously a unique solution, consistent, and this is also consistent. So ui less than wj is a basis of uw respectively. So they are individually linearly independent. So by the definition of linearly independent, you can observe all constant will be 0, all scalars will be 0. Similarly for w subspace, all scalars will be 0. Since a1 a2 equals to b1 b2 equals to all are 0 vectors, so ui wj are linearly independent. That is, B set is linearly independent. Since B is linearly independent, so B can be written as the linear combination of B. So B is the basis of B. Hence, dimension of B can be written as M plus L. So dimension of B equals to dimension of U plus dimension of W. Now another theorem: the row rank and the column rank of a matrix are equal. The row rank and column rank of a matrix are equal. Suppose any matrix A1, 1, A1, 2, dot, A1, N, that means M cross N matrix. The matrix of Aij, the types of an arbitrary M cross N. Then the row of A, R1 equals to this, R2, this is R3, and this is the M row. Okay. Suppose the row rank of is R, and these R exist linearly independent rows of A vectors, which will be form the basis of the row space. Suppose the following are the row space, and the row space S1 equals to B1, B1, and S2 equals to these vectors form a basis SR. So each row can be written as the linear combination of the basis vectors. So R1 can be written as this, R2 can be written as this. Similarly, Rm also can be written as this. So the ith elements of each of the vectors, A1 ith elements will be this. So second row, third row, mth row, ith element, which can be written as the just these column vectors, and the coefficient bi1 is the common, and k1 these column vectors and these column vectors. Similarly, last column vectors and bri are the common for each I equals to 1 to n, so that each column of A is linear combination of the R vectors. Here, how many vectors? R vectors. So R vectors, these vectors, these vectors, these vectors, these vectors are times of vectors. This implies the column space of matrix A has the dimension at most R. Thus, the columns rank will be less equals to R. Hence, the column rank of A less equals to row rank of A. Again, considering the transposing matrix AT, we obtain the row rank of A less equal to the column rank of A. In this way, the rank, row rank and column rank are equal. Now, what will be the row rank and column rank? This is the definition. Row rank, let Aij be any M cross N matrix of our field F, then the row rank of A written as the row rank of A is the dimension of row space of A. If R1, R2 dot dot Rm is denoted by the rows of A, then row rank of A can be written as the dimension of linear combination of the row rank. Similarly, the column rank also can be defined by C1, C2. Now, another important theorem. Let U and W be finite dimensional subspace of a vector space B. Then show that dimension of U plus W equals to dimension of U plus dimension of W minus dimension of U intersection W. Let U and W be the two subspaces. So U intersection W is a subspace of both U and W. Let dimension of U equals to M, dimension of W equals to N, and dimension of U intersection W equals to R. Suppose B1, B2 dot dot Bn is a basis of Br. Okay, basis of U intersection W, and since U intersection W is a subspace of both U and W, so we can extend the basis of U intersection W, then form a basis. That means B1 B2 dot dot Br, U1 U2 dot dot Um minus R of U, and a basis, another basis B1 B2 dot dot Br, W and W2 dot dot Wn minus R of W. Let B be another set B1 with B1 B2 dot dot Br, U1 U2 dot dot M minus R, and W N minus R. So hence we see that B has exactly M plus N minus R elements. So the theorem will prove if we can show that B is the basis of U plus W. Since Bi use A is the basis of U and it generates U. Also the since Bi Wk is a basis of W, so Bi Wk generates W. Then the union B equals to Bi use A, Wk generates U plus W. Now we sufficient to show that B is linearly independent. That means the linear combination one with the scalars Ai, Bj, Ck, we can write B equals, let B equals to this linear combination. By equation 1, B can be written as minus C1 W1 C2 W this. Suppose Bj use A, Bi use A is a subset of U, so B belongs to U. And Wk set also belongs a subset of W, so B belongs to W by equation number 3. Therefore, B belongs to U intersection W. Say again, since Bi is the basis of this, so there exist scalars d1, d2, dr, for which we can write the linear combination of B, B1, B2 dot dot Br. So this B equals to minus B1 W1. So from the both sides we can write this one. But Bi Wk is the basis of W, so Bi Wk is linearly independent. Hence from 4, equation 4, we can write all scalars are 0 individually. So putting C1 C2 equals to Cm M minus R in 1, we get this linear combination. Okay, but Bi use A is a basis of U, so Bi use A is linearly independent. So from equation 5, all scalars are 0. Since 1 implies that Ai, Bj, Wk are all 0, where all scalars are 0, but B is the basis of U plus W and is therefore the set B, Ui use A, Wk are linearly independent. So dimension of U plus W what? M plus N minus R. So dimension of U plus W equals to dimension of U plus dimension of W minus dimension of U intersection W. This is the actually proof. We can prove this theorem by another method. If W and W2 are two subsets of finite dimensional, this we can use the same method here. Okay. Say this is another method. You can apply this method to prove. Okay. Very easy method. This is another method to prove the theorem. Dimension of U plus W equals to dimension of U plus dimension of W minus dimension of U intersection V. This is the sum outline series from book. Okay, very easy theorem. And now we'll try to solve some examples, including basis and dimension and linear combinations. Determine the whether the given set of vectors of a basis R3 over R first one this and second one this one. We have to test the basis. Let us form the matrix with the given vectors and reduce it to echelon form. That means first vector first row, second vector second row, and third vector third row. Now by in echelon form, just subtracting second row from first row, subtracting first row from second row, so we get this one, and similarly this one. Now this adding first second row and third row, we get this one, which is in echelon form. Since the echelon form has three non-zero rows, the given vectors are linearly independent. Now, since the given vectors, set of vectors are linearly independent, and the set of vectors basis of R3. These three are the basis. Similarly, for the second one, first vector, second vector, third vector, and by an echelon form, we get this. That means multiplying 2 with first row and subtracting from equation 2, we get this one. Similarly, we get this one. Okay, multiplying by 10 with first row, then subtracting from third row, we get this one. So by echelon form, we observe that third row is 0, which is in echelon form, and the echelon form has a non-zero rows, 2 non-zero rows. Okay, so and 1 is 0 rows. This is why it is linearly dependent. So by the definition of basis, the vectors must be linearly independent. So it is not a basis. Now find the dimension of the subspace generated by the set 1 to 1, 3, 1, 1 this. That means same as before. This is the first vector, first row, second vector, second row, and third vector, third row. Then this 3 cross 3 matrix, now solving by echelon form, multiplying 3 with first row and subtracting from 2, we get this, and subtracting from 1. So we get this one. So which is in echelon form, has the dimension of the subspace generated by S is 3, because 3 non-zero rows. Now, another example, W ABC such that ABC belongs to real number, and an equation twice A plus twice B plus twice C equals to 0, find a basis and dimension. Let ABC belongs to W implies this equation, given equation. We have only one equation with 3 unknowns. Okay, so free variable, what will be? Number of variables minus number of equation equals to 2, which are BC. Now let, if B equals to 0, then and C equals to -1, then we get A equals to 1 from equation 1. Just putting these values. Now if B equals to 1, C equals to 0, and we get A equals to -1 from this equation. So basis of W, what will be? What will be? 1, 0, -1, and -1, 1, 0. So dimension what? Number of basis vectors, 2. Now find the basis and dimension of the subspace W of R3, where W equals to ABC such that A plus B plus C equals to 0, and ABC such that A equals to B equals to C. Note that W is not in R3 space, because 1, 2, 3 doesn't belongs to W, thus dimension of W must be less than 3. Note that U1 equals to 1, 0, -1, and U2 equals to 0, 1, -1 are two independent non-zero vectors in W. Thus dimension W equals to what? 2. So U1, U2 are form a basis. On the other hand, vectors U equals to 1, 1, 1, 1, 1 belongs to W, and any vectors small w belongs to capital W has the form with the scalars k, k, k. Hence, the scalar multiplication can be represented. Therefore, U spans W, and dimension of W equals to what? 1, because only one basis vector. Now, show that the vectors U1, U2, U3 spans R3. We need to show that an arbitrary vectors B, A, B, C in R3 is a linear combination of the given vectors U1, U2, U3. So ABC equals to can be written as the linear combination of this with a scalar X, Y, Z. Now, so this X plus Y, Z equals to A, and these 3 equations from the above linear combinations. Now, by an echelon form, the subtracting equation 2 from 1, 2 from 1 from 2, and 3 from 1 from 3. So we get the solutions. The above system is in echelon form and is consistent. So in fact, X equals to Y equals to 0. That means is a solution. So we obviously say that U1, U2, U3 are the basis of R3. So span R3. And that means the given vectors can be represented as a linear combinations of the vectors, basis vector. Now show that R3, these three vectors, even the generates 3. That means same as before, we can write the linear combinations and this form the system of equations. So three equations with three unknowns. Now solving, we get the XYZ values. So you obviously say that V1, V2 are the linearly independent vectors, basis vectors. That means S span R3. So another example, find the basis and dimension of the solution space W with the homogeneous system 1, 2, 3. There are three problems at a row. Now transform the from the equation 1, transform the in echelon form. This is the first equation with 5 unknown x, y, z, s, t. 5 unknown, 3 equations. But we can transform it in echelon form. How? Subtracting 1 from 2 and subtracting 3 times of 1 from 3. So we get, we observe that 2 equations are unknown and 3 last equation become 0. So the system is in echelon form has non-zero equations in 5 unknowns. So here the system has the number of variables minus number of equations in echelon form. So equals to 3 free variables. So YST are the free variables. So putting y equals to 1, s equals to 0 and t equals to 0, we obtained that z equals to 0 and x equals to -2. So e equals to this is the basis of W. Similarly, y equals to 0, if y equals to 0, s equals to 1 and t equals to 0, then we get z equals to -2 and x equals to 5 from the equation of echelon form. So b equals to, this is another basis of W. Again, if y equals to 0, s equals to 0 and t equals to 1, then z equals to 2 and x equals to -7. So these another basis of W. So the basis of solution space is UBW. So dimension will be 3. Now similarly, from the second one, we can form the matrix with 4 unknown and given 3 equations. We observe that last equation is 0. Hence, the corresponding, we can write the equation x plus twice y plus z minus twice t equals to 0 and 2z plus t equals to 0. So free variable what? 2, because number of equations 2 and number of variables what? 4. 4 minus 2, 2. Therefore, yz are the free variables. If y equals to 1 and z equals to 0, then t equals to 0 and x equals to -2. We get the basis. Similarly, putting this value, we get another basis. So these two are the basis. Okay. Similarly, we can reduce the third one. Now, if ABC are linearly independent, then show that a plus b, a minus b, a minus twice b plus c are also linearly independent. So by the definition of linearly independent, we can write that linear combination equals to 0. Now, from this, we can write 3 equations. We can observe that x equals to 0, y equals to 0, z equals to 0. That means every scalars are 0. Hence, the given vectors are linearly independent. Now, if u and w in the R4 space ABCD, b plus c plus d equals to 0 and w equals to b plus c plus d, BCD, BCD, and such that a plus b equals to 0, c equals to twice d. Find the basis and dimension of one u and dimension of w and also u intersection w. Now to find the basis, you have to find out the solution of the given condition b plus c plus d equals to 0. The dimension of the solution space is the dimension of u. That means n minus r. So number of variables minus number of given equation. Only b plus c plus d is the single equation. This is why 3 variables. So free variables are SAD. Now putting a equals to 1, c equals to 0 and d equals to 0, then b equals to 0. So the basis will be 1, 0, 0, 0, u1. Again, similarly, putting this one, we get u2 and next third basis. So 3 bases. So dimension will be 3. Similarly, to find the basis of W, we have to find out the solution space satisfying the 2 equation. So given equation is 2 with 4 unknown. That means the dimension of W will be 4 minus 2 equals to 2 and the free variables will be BD. So the putting b equals to 1, d equals to 0, we get c equals to 0 and I equals to -1 from the given equation. So basis will be this W1, and from the second one W2. So from the third one, to find out the basis of U intersection W, we have to find out the solution which is satisfying the both the condition. That means 3 equations with 4 unknowns. So dimension of this will be 4 minus 3, and free variables will be only d, because free variable 1. So putting d equals to 1, we get c equals to 2, b equals to 3, and I equals to 3 from here. So the dimension, the basis of this will be this. Now find the homogeneous system whose solution of set W is generated by this. Since the three sets can be written as the linear combination of x, y, z, W. So 4 equations with 3 unknowns. So we can observe that in Echelon form, now another example, if W is the space generated by the polynomials of degree less equal to 3, then B1 equals to polynomial this, B2 equals to polynomial this, and B4, there are 4 polynomial, find the basis and dimension. First find out the coordinate vector U relative to the basis T cube, T square, T1. That means 3 degree, third degree polynomial. So B1 equals to just coefficient 1 minus 2, 4, 1, 1 minus 2, 4, 1. And B2 equals to what will be 1, 0, 6, minus 5. And B3 what will be 2 minus 3, 9 minus 1. And B4 what will be 2 minus 5, 7, 5. So from these 4 vectors, we can form matrix, 4 cross 4 matrix. So by echelon form, we can subtract 1 from 2 and 1 from 2 times 1 of 1 from 3, and subtracting 3 times of 1 from 4. 2 times of 1 from 4. We get this one. Similarly, to make this 0, we have to subtract 2 times from the second one, second row, 2 times. This is why the non-zero rows are 2. The non-zero rows are B1 equals to this and B2 equals to this. And B1 can be written as T cube minus 2T square plus 4T plus 1. Similarly, B3, 0 into T cube plus 1 into T square plus 1 into T minus 3 for the basis of W, and dimension what will be 2, because 2 bases. Similarly, another example, if the vectors, these are the vector space in R3 are linearly dependent, find the value of A. Suppose x, y, z are belongs to any scalars belongs to R. Consider this can be written as a linear combination of this. So we can form 3 equations. So just solving, we can find out the value of K. So substituting this value, we get different scalars. Since the given vectors are linearly independent, hence K doesn't equals to 0. So required values of A are 0, root over 2, minus root over 2. Now we can solve this problem easily. If ABC are linearly independent vectors in vector space, then prove that A plus B plus C plus C also linearly independent. Just making linear combinations and solving x, y, z, we get 0. So which proves that A plus B plus C plus A because are linearly dependent. Now the polynomials, similarly, we can solve this problem as previous example. You can be written as the linear combination of the all polynomials. Now the coefficients, the equations can be written as equating on both sides. We can write x plus 2y equals to 1, this equals to 4. Okay, so we observe that just by in echelon form, we can solve this one. So we can be written as linear combinations. On the other hand, we also prove this problem since we can write a linear combination of this. So u equals to xu y w. So where xy belongs to. Similarly, conditional equality, and we get by in echelon form, we get x equals to 2, y equals to -1. So can be written as linear combination. Find for what value of k the vectors is a linear combination of the vectors this and this. So w equals to 1k5, set w equals to what xu and yb. That means linear combination. Just w equals to what 15k, and equating on both sets, we get form two sets of equations. So these equations can be written, make this just adding, okay. And this is the just adding this one we get, but the last two equations from last equations equals to 3. So and putting x equals to 3 here, we get k equals to -8. Similarly, write the matrix E as a linear combination of the matrix this. Okay, very easy problem. Just we solving, we observe that y equals to, x equals to 3, y equals to -2, and z equals to -1. Since the values of also satisfy the last equation, they form the solution of the system. Hence, equals to thrice a minus twice b minus c. That means it can be represented as a linear combinations. Similarly, we can solve this also. Now, if be the vector space of a polynomial degree less equal to this, I can determine UBW belongs to independent or dependent. The set of linear combinations, this, and we can coefficient, equating the coefficient, we get the system of equation, 4 equations. Now solving, just subtracting 1 from third, 5 times of third of 1 from third, okay, and 5 3 and subtracting 1 from fourth equation, and adding that 3 times of equation 1 with second equation. So in echelon form, we observe that x equals to 0, y equals to 0, z equals to 0. So u plus all scalars are 0. This is why UBW are linearly independent. Similarly, second one, all scalars are 0. So polynomials are linearly dependent because there are 4 equations with 3 unknowns, but one equation, what will be cancelled? Only in echelon form we get only 2 equations. So finally you get these 2 equations. This is why linearly dependent. Now very important example. This one, let U and W be any two subspace of R5, where U equals to this, B equals to this, and another one, W equals to this. Find dimension of U plus W and dimension of U intersection W. Here, U plus W form a basis whose rows of the given vectors are. How many rows? First row, second row, third row, fourth row, fifth row, sixth row. 6 row here with 5 elements. So just subtracting 1 from second row, subtracting 2 times of 1 from third row, subtracting 2 times of 1 first row from fourth, subtracting first row from fifth row, we get this. And similarly, 3 times. Okay, these 2 can be removed by multiplying first row with 2, then subtracting. So in echelon form has 3 non-zero rows. Dimensional U plus W equals to what? 3 non-zero rows. This is why. Now we'll show that dimension of U and dimension of W can form 2 matrices. So dimension of U here, how many rows? 3 rows and 5 column. So in echelon forms of subtracting first row from second one, and 2 times of first row from third row. So in echelon form we observe that 2 non-zero rows. So dimension 2, and from W set of vectors W in echelon form, we observe that third row 0. This is why dimension of U equals to 2 and dimension of W what non-zero. This is the non-zero rows, 3 non-zero rows. So dimension of U plus W equals to what? From theorem, dimension of U plus W, dimension of W minus dimension of U intersection W. So putting these values, we get dimension of U intersection W what 2. Because dimension of U plus W what was 3. This is why we get this one. Now consider the following subspace of R5 UW similar process, we get the solution. Okay, this is left for you. So this is the homework for you. Determine whether you be linearly dependent where this and this, just using echelon form. So thanks to everybody. Today we will discuss this, and this is actually a review of a vector space and solve some theorems, and we also solve some examples. Now some application of vector space. Actually, it has a vast application in electrical engineering and in also calculus, solving differential equation, linear differential equation. Linear differential is the form. This is the form of linear differential equation. Now, how we can use the vector space? Show that both y1 and y2 are solutions of the second order differential equation y double dash minus y equals to 0 for the function y1 equals to this, and differentiation of y1 what will be e to the power x, and double differentiation root will be x. So this given differential equation can be written as this. Now y1 equals to x is the solution of the differential equation because it satisfies the equation. So it implies that y2 also the solution of the differential equations. Now these two equations from the first that the vector space of twice differentiable defined on the entire real line, the solution y1 equal to y2 are the linearly independent solution. This means the solution of c1 y1 c2 y2 equals to 0, where c1 equals to what, c2 equals to are all scalars. The second observation that linear combination of y1 y2 also solution of the linear differential equation. So to see this, y can be written as a linear combination of c1 y1 c2 y2. This is the solution of the above differential equation. Then y can be written as this c1 e to the power x, and the differentiation of y equals to this, and double differentiation will be this. So substituting these equations in the given original equation, we observe that this equals to 0. So y equals to this is a solution. So these two observations are generally the next theorem. This is actually this is the definition of Wronskian to test the linearly dependency or independency of the solution of differential equation. Okay, this is the formula. And suppose for finding the Wronskian set 1 minus x, 1 plus x, and 2 minus x is what will be? This is the given y1, y2, y3, and differentiation of y1, y2, y3, and second differentiation. So the Wronskian will be this, just determinant. So the Wronskian is identically equal to 0 because it is 0 for any values of x. The Wronskian is a part not identically equal to 0 because for every values of x for which the Wronskian is non-zero. Now linearly dependence, what? Let y1 yn dot b and be the solution and number of solutions of nth order linear homogeneous differential equation. This set is linearly independent if and only if the Wronskian is not identically 0. So if Wronskian is not equal to 0, then linearly but independent. Now we can test these differential equations. This is the solution. Similarly, we can test the set of solution of linear independence of the third order differential equation. Just using the formula of Wronskian, we can observe this. So thanks to everybody. I hope everybody will enjoy this class and practice more and more. So if you do practice and try to understand and follow the books of reference, I hope everybody will understand better. Thanks to everybody.